levels. We have the operating system itself, and then the container runtime, Docker or say Rocket. And it looks like a graph that's very similar to the one we saw previously, right? We have clear differentiation of responsibility. Unfortunately, it isn't that simple, and if we take a closer look inside, we'll see why. If we take a look inside of the container, we actually see now that each container itself, in fact, contains the packages that we're relying upon, and perhaps even a package manager, and even sometimes the user space of an operating system such as Ubuntu. So now the question becomes, who's in charge of managing these packages and these package managers when a security vulnerability occurs? And even more so, we'll notice that sometimes packages are shared across multiple containers. So you can see here we have package A and C that are shared in both of these containers, B and D obviously being different. If there's a security vulnerability in package A, now I have to remember, whoever I am, to update not only container 1, but container 2, and perhaps 3, 4, 5, 6, 7, 8, 9, and 10. And that's easy for me as a single engineer to forget to update one of these containers, and whoops, now there's a major vulnerability. So, this is all a problem in theory, but in practice, how really common is it to actually see this level of issue with containers? Well, we've seen some major issues these past year or two come out. We have Ghost, which is a buffer overflow bug affecting get host by name, and it lets you make application calls at a privileged rate. We've currently, using our beta software we're going to be demoing today, we've analyzed a couple million images on Quay. What percentage would you, as the audience, think are affected by Ghost? Anyone?
50 plus.
30%? 50? 75%?
I'd say 85.
Okay. 66% of all images on Quay that we've analyzed, and that's millions of images, are affected by this. And this is a privilege escalation. That's a huge number. Of course, we've all heard of Heartbleed, and this allows people to get access-sensitive information, keys, and things inside of a running application. What would you, as the audience, think is this number?
85.
Keep in mind that Heartbleed came out last year, so we've had a good amount of time.
40%. 35.
80%. 80% of the images that we've analyzed on Quay, and this is millions of images, so it's not a small sample size by any means, are currently affected by Heartbleed. And this is something that's been out for over a year. And we've all heard about it, we've all rushed to patch this issue. And yet, today, we still see this is a major, major problem.
Is that like just looking at the latest tag?
You'll see when we get there, but yes. So, why is this happening? We all are diligent engineers and DevOps people and DevOps people. Why is it still this case? The problem is this. Most containers are built on the same base layers. So if we look at the Docker Hub, you'll see that these are the 5 most popular images, and they are base layers. They form the foundations of all the containers that we're running in production. And in fact, if you look at Ubuntu, this has been pulled 29.5 million times. That's an insane number. And a lot of us are using the Ubuntu-based image. So, how do we make this better for developers? Obviously, we're not meeting our due diligence here to solve this problem. And it is a huge problem because, as we all know, these vulnerabilities can lead to real-world exploits that people are doing today. The answer, automatically detect these things and let developers know that their images are vulnerable. So with the system that we're announcing today in this room, and then we will be announcing more generally in the coming weeks, we check every new image pushed to our registry for vulnerabilities. We also check every existing image against new or updated vulnerabilities.
Are we allowed to talk about it outside of
Yes, you are. Yeah, this is just a preview. The only reason I'm saying it's not generally announced is because it's beta, so things may change, details may shift, etc. But it's pretty much there. And the most important aspect, we notify developers who are using our system when an image is vulnerable, even if they're not looking at our user interface on a day-to-day basis. So, how does this work in practice? Well, every time a person pushes an image to Quay or uses our build system via Git or GitHub or whatever, what have you, to build, the image gets pushed into Quay, and at the same time, our analyzing system, Claire, which Quentin wrote and we'll be giving a technical deep dive into, analyzes the system for the images for vulnerabilities, and if any are detected, we show it in the user interface, and we also send out a notification via our notification system, whether that be via Slack or email or a webhook even. And this actually lets you set up some very interesting integrations, in particular the webhooks, such that you could even say have it so that an image that would be automatically deleted if it has a vulnerability, or retagged or something. So that's all cool in theory. I'm going to give a quick demo. Just one caveat: this is beta. I apologize for bugs, and of course Murphy's Law. Blah blah blah. And this is really tiny, so I'm going to make it bigger. See if I can do that here. So this is a Quay running on my local machine. And I'll go into my repository here. And right before the talk, I pushed an image, and it's this latest image here. And it got analyzed by our vulnerability system, and lo and behold, the image has vulnerabilities. This flag column, subject to change, is our new column that we're showing in the tag view once we launch this feature. And it'll let you know if that tag has any vulnerabilities within the image with a color code indicating the highest priority that we've detected. So in this case, there's a medium vulnerability. And if I click it, you can see here that the vulnerability is an issue with bind, CVE 2015-2730. We get a nice little description here of what the vulnerability is, but it's kind of small, so if I want some more information, I can just click here and hope the internet is working because of Wi-Fi, and lo and behold, it does. So I get to go to the Red Hat website, and it tells me more details about what's going on with that vulnerability. So now I, as a developer, can just look at my images or tags and see what vulnerabilities there may be. And this will be updated in real time. Similarly, because we have this information, we can also show the packages that are available within an image. So in this case, I've clicked into that tag's image, and I can see all the packages that are installed under that image, the operating system from which they came, and any of the versions of those packages. Now, this in and of itself isn't as useful, but if you need to do some sort of security auditing outside of our own system, or you're just curious, this is very interesting information to have access to at any given time. Now, that's great if I pushed an image and I see the vulnerability. What happens if a new vulnerability comes out when I'm not watching? Well, what I can do is, and I'm going to run a little script to add a high-level vulnerability here. And we have to wait a few seconds for the system to pick it up. So hopefully this works. I'll just reload here. Okay, and now you can see the flag is turned red because it's detected a high-level vulnerability in my image. And you can see now I have the two vulnerabilities here, including this new one here that's of high level. But if I'm not watching the UI, if I'm not sitting here all day incessantly refreshing the UI, which I shouldn't be doing, how would I know that this vulnerability has come in and now my image is even more vulnerable than it previously was?
Webhooks?
Webhooks and notifications. So if you go to the settings page here, you can see I have two event notifications set for package vulnerability found. One to set up a local notification in Quay, which you can see up here if I click that bell, and one to set up a Slack root notification. This is actually the one that I find most interesting, and you can see here it's very tiny. But you can see here, I just received at 2:42 p.m., which is, or 2:47 p.m. rather, which is a minute ago, that a high vulnerability was detected in this repository. I can see which vulnerability it was, and clicking it will take me to that information on the tracker, which tag and which repository. And this is really easy for me to set up, and now means that I, as a developer, will know immediately, because I'm usually in Slack, if there's an issue that occurs. So these pieces together means that I have a very significant system for me to track and keep on top of issues as they occur in real time. We also, not demoed here, have the ability that if there's something that comes out, such as Heartbleed, a critical vulnerability, we can actually mark that level up as what we call DEFCON 1. And in fact, any repositories that have a DEFCON 1 will receive an email automatically from our system, regardless of the notification setup, saying to the repository owner saying, you have Heartbleed in your repository, please fix, such as that. So now that we've seen how this works, click here, my coworker Quentin is going to give some background and details of how the system actually works. And I believe there's a question in the back, so before we continue.
Yeah, does the system know at all if fixes are available?
So Quentin will be giving some more information about that right now. And before he starts, if you do have any questions, just continue to please feel free to ask them. We're happy to give as much information as we can.
Cool.
Quentin?
So, hey. So this design has been led by one goal, which is analyzing millions of containers in a minimum amount of time and cost. So to do this, we could not run any of these containers. It will be too slow and also insecure. Instead, what we do is extracting the necessary knowledge from the static content And because we want to analyze them only once, we will extract any information which will allow us to actually determine their vulnerabilities right now, but also in the future. So so what is actually an image content? It's basically a stack of layers, and each layer is some metadata like ID, parent ID, command, and variable environment informations. And more interestingly for us, a file system diff, which is an archive containing like every file that has been added, modified, or removed. And so when someone pushes an image to Quay, we will analyze it layer per layer and extract two informations. The first one is the operating system of the layer. The second one is a package list. So we will usually find the operating system in files like etc/something/release or even etc/apt-sources.list. For the package list, we may find this information in vorlib pkg status for Ubuntu and Debian, or for CentOS in vorlib RPM packages as a Berkeley database. Now, we may not find this information if the layer does not modify any package or does not modify the operating system. But if it does, we will find the entire package list in these files, and that's not exactly what we want. So we'll compare that entire list with the list of packages that the parent has, and then we'll have like exactly which packages a layer add, remove, or upgrade. So at the end of a layer analysis, what we'll have is an improved diff actually, with the metadata, the file system diff, but also the operating system and the package list diff. With all this diff together, we'll be able to reconstruct the entire information about an image. So we considered storing all this diff in a traditional database, but we were concerned about usability and flexibility, and we decided to store everything in a graph. For that, we are using Kelly, which is an open source database maintained by an ex-Google employee. It's written in Go, just like our tool, so we can use it as a library. And it also supports multiple backend stores, like Bolt, SQL, MongoDB, in-memory store if you want to store ephemeral data. So it's very nice because you can deploy our app like in very different environments depending on what you already have. Through this example, I will show you how our graph looks like and how do we actually use it. So a graph contains 4 kinds of informations: layers, their archives, their contents, packages, and vulnerabilities. Let's get started by analyzing the first layer, which only sets some metadata. So we'll create a node with its ID and then a node for its content. As it only sets metadata, the archive will be empty, so we won't find any information except the checksum of an empty torgz, which is pretty not useful for us. And then we'll move on to the second layer, which actually imports Ubuntu in the container. So we'll create a node, link it to its parent layer, and analyze its content. But here, we will actually find the operating system. And also, we will find that it installs OpenCL 1.2 in the container. Then, we'll analyze the third layer, which does some kind of package upgrade. So, same thing. We'll see that it actually removes OpenCL 1.2 and replaces it with OpenSSL 1.3. So it actually did the upgrade of OpenSSL right here. We'll go through the 4th layer and the 5th layer that just set metadata. So just like the first layer, it will not give us any more information. So at this point, we fully analyze an image, which is great. Internally, the tool will create 2 synthetic versions, package versions, which is 0 and infinity. So they both are useful for database consistency, but the infinity version also serves a particular purpose that I will talk about a bit later. Now, something is missing right here, vulnerabilities. So the graph will be updated periodically from distribution-specific vulnerability trackers. For instance, Ubuntu CA tracker, the Debian security bug tracker, and Red Hat Erratas. Each source has their own format, and therefore we have one parser for each of them. But because we use distribution-specific sources, our system can be very accurate because each distribution knows exactly when they patch a vulnerability and when they backport patches for vulnerabilities. So yeah. The system knows about 16,000 vulnerabilities right now, including over 5,000 high and critical vulnerabilities, which includes remote code execution, privilege escalation. So that's a lot of vulnerabilities, I think. So back to our graph. We'll now have vulnerability right here with its ID or link with the subsonial priority. And we can see that it is actually fixed in OpenSL 1.3, which means that every version prior to OpenSL 1.3 are vulnerable to that vulnerability. Now, what if we want to know the vulnerabilities of our image up there? We will through the parents, like this, to determine the list of packages of that image. So the first layer does not add any package. The second one adds OpenSL 1.2, which is replacing the third layer. And the fourth and fifth does not modify the packages. So at this point, we know that our image only contains OpenSL 1.3. And we'll go through its successor. Like, the only successor here is the OpenSL Infinity version. And it does not fix any vulnerability. Therefore, this image does not have any vulnerability. But what now if I modify slightly our example and drop the apt-get upgrade and go through immediately the command execution? Now, I won't analyze again the first and second layer because we already know them. But I will analyze the sixth one here. And if I try to know the vulnerability of that image, I will determine, just like before, the packages of that image. It will be OpenSL 1.2 here. I will go through its successors. And here, I'll see that OpenSL 1.3 fixes the vulnerability, which means that OpenSL 1.3 is vulnerable, and therefore our image is vulnerable to that vulnerability. That's about it. There is one more thing. Why do we use the Infinity version there? It's useful because imagine that there is a vulnerability that exists that affects OpenSSL but has not been fixed yet. In that case, we will just virtually link that vulnerability to the latest version over there. And it will basically mean that every single version of OpenSSL are vulnerable to that vulnerability. That's why we use that. That's it.
So we've seen how the system actually does the vulnerability checking and tracking. This system is going to be open sourced. It's going to be used via Play.io hosted and our enterprise version on premises. It will be packaged as well as a simple Docker run, Docker container, which can be run via Docker run. And everything that we do currently and could be done will be accessible via an HTTP API. So we're hoping once it's launched in a week or two that we can get some feedback, people adding new package distro support, and hopefully other registries will pick this up to improve the security of the web as a whole. So, any questions about the system before I make a brief shout out to some stuff we're going to be doing here in the near future? Yeah.
So there are a lot of language-specific package managers now, which don't have the same publication model for vulnerabilities. Like, what are your thoughts on how do you start on that problem? Because that's
So you can actually insert your own vulnerabilities into the system through the API. So if you deploy your own stack of this app, you may say, oh well, this app contains a vulnerability by yourself, not using whatever other database sources. Or you may also define your own database source because you can hack the application and add your own data system, which is pretty straightforward.
And as for language-specific package managers such as pip and Ruby gems, we're investigating support for it. As it currently stands, since the data isn't great, you'd probably have to have somebody manually collating it. There are people that are doing this, and so we have been looking to maybe just straight up web scraping a few certain areas. It's not great. Our hope is this will partially drive adoption of more formalized metadata structures that can then be read by tools such as Claire, such that it could be done in a more automated fashion. But again, since the whole system will be open source, our sincere hope and belief is that everyone will pick this up, and we'll get support for not only all of the distros, all the language-specific stacks, but maybe even other aspects that maybe even Docker itself, Rocket itself, things that where you can basically check your whole stack top to bottom.
Will it be called Claire, the open source version?
Yeah.
Yeah.
Yeah. It'll be under github.com/CoreOS once we open source it. As I said, it's probably going to be about 2 weeks until we officially put it out there. Any other questions? Okay, so a brief shout out. We're going to be running a summit here in New York City on December 2nd and 3rd about enterprise adopters of containerized applications and containers and how it helps their business. There's going to be a lot of great speakers. There are invites available at tectonic.com/summit. I know this is a bit of marketing speak, but it's going to be a great summit. So if anyone would like to come, just go to that URL. And yeah, and any other technical or other questions, feel free to come grab us. We'll be here for another 15, 20 minutes at least.